Okay, so welcome everybody. It is my pleasure to introduce today Gabriele Sicuro, who is a friend and long-time collaborator. And Gabriele did his PhD in University of Pisa under Sergio Caracciolo, and then held postdoctoral appointments in Brazil and in Sapienza under Giorgio Parisi, and later on in École Normale Supérieure and EPFL in the group of Florent Zaccala. Since 2021, he's a lecturer in disordered systems at King's College London. And the title of his talk is Classification of Fat-tailed Clusters in High Dimensions. Please, Gabriele, go ahead.
Thank you, Matteo, for the introduction, and thank you for the invitation. So as I was mentioning before, this talk will be about a subject that was about a topic that was developed with Urte Dometita, that is a PhD student at King's, and Pierpaolo Vivo, who is a collaborator of mine here at King's as well. And will be about, indeed, the problem of classifying clusters that have fat-tailed distribution in high dimensions, the title say. And the motivation came from the fact that there were many results, interesting results. I will try to give a short overview of them about the problem in the case in which we have Gaussian clouds. And there were also some discussion about how robust, let's say, the Gaussian picture, the Gaussian design is. So that's why we try to stretch a little bit this hypothesis and see how things change when you have power tails. Okay, so this is the outline of the talk. I will just fix the notation in the first part. I will just introduce in classification learning. Probably you all know what these things are nowadays. Then I will introduce this very widely studied Gaussian mixture model, and discuss some results that we obtained on this actually in the past with another group about the classification of Gaussian clouds in high dimension with the perceptron. Then I will discuss a little bit this new approach that we tried to produce clouds, the fat tails, and comment on some universality results that were produced recently, and we try to see how generalized to this kind of more general setting, more general family of distribution, and then some conclusions. So I think there is no need for me to stress that machine learning is attracting a lot of attention, and as you all know, many people are working on that, and many kind of tasks can be performed by this huge architecture that are trained to drive cars, as you know, or recognize digits or label photos and so on. And classification tasks in particular are classical tasks that you can try to perform with this architecture. So there are plethora of things that you can try to do. You can try to take an architecture like the one this in the figure, that is some feed-forward network in which you have an input, and each layer performs some linear followed by, for example, simple linear and simple element-wise nonlinear operation of the input until you get some output. And the output that can be in classification task is typically a label, something that tells you what was fed in the network. And this is a general framework in which many important tasks fall, for example, facial recognition, song recognition, diagnostic test, or document classification. For example, you can feed a text and ask to a network to tell you if it's spam or not. And of course, many type of approaches have been used to solve this problem in general, and you can, let's say, think about many classical papers dealt with this, including this pioneering work that was done by Lecan in the 90s, in which was trying to train a one-layer, actually, neural network to recognize handwritten digits. And you know very well as well that now this kind of architecture can achieve superhuman performances. So the error that these machines make in labeling, for example, handwritten digits or things like this can be above, can be below the one that humans achieve in the same task. Overall, this kind of architecture, a large portion, a large class of this architecture have this general structure. You feed in the network your input, for example, the image, for example, a picture of a handwritten digit, And there are many layers that perform, as I was saying, kind of simple operations with nonlinearities and so on. And at the end, they produce a representation of the input that here I call the x theta view, where theta is express the fact that there is some dependence on parameters in the networks that I call theta indeed. And this is a representation that is produced at the last layer that depends on the input. And finally, what is done is a classification of this representation. So the last piece of the network just decide what the input is, depending on this representation that's been produced by the network. Typically, this classifier works in this way. We will be interested in classifiers that work in this way. They take this input. You see my mouse, no? Okay. The classifier takes as input this feature vector, x theta of u, applies to it a matrix of parameters, w, and this square root of d is just a rescaling with the dimension for, let's say, to keep things order 1. And then it applies overall nonlinearity, also obtain a new vector and applies a nonlinearity element-wise to produce a label, y hat. And of course, what you would like is that your y hat is the good label of what you fed in the network. Okay, so this is, I would say, very general. This is a very general framework. So there are parameters inside the bulk of the architecture and parameters in the last layer. I use different letters to distinguish them. I call theta the parameters inside, and w the parameters in the last layer. And what you want to do is to find the best parameters to perform a task. And in principle, what you should do is to try to minimize some cost function on the probabilistic law that generates the input and the associated labels. So there is this, you imagine that there is a law P of Y U that generates these pairs. So generates, for example, a picture and the corresponding label. And in principle, what you would like to do is to take some kind of error measure of the performance of your network that is expressed in terms of this loss function L, and minimize the expectation of this loss function L with respect to this probability P, tuning the parameters properly, so trying to make this fit of the parameters. Of course, this is not something that you can do in general because you don't know this law. What people do is to say, okay, I pick a data set, so a collection of possible inputs U and desired label Y. And what I do is try to minimize this empirical loss, this empirical risk, saying, okay, I try to minimize the average of this loss over all possible elements of my data set. And so I try to find the best W and theta that give me the smallest possible value of this loss. So the structure of this loss that I will use is, you see, it's a function that depends on the label and on what is fed in the classifier. So it's what appears here is what people sometimes call pre-activation, is Wx divided by square root of d. And so the dependence on the parameters is inside this second piece. Okay, of course, this task is not trivial in general. You might face rough landscapes, and it's not obvious that you are able to find this minimum. You might have you might expect convergence problems and so on. And there is a lot of debate about the fact that despite all these theoretical, let's say, expected difficulties, this machine anyway perform very well when you do this. And for the theoretical analysis, doing this analysis, this study in general is quite hard, and therefore we will focus on a much simpler architecture. Essentially, we will focus on the classifier, just the classifier. But this was just to give you, let's say, to fix a little bit the notation. And before studying our simple architecture, I want to say some words about what is produced here as feature vector once you train this network. Because what you expect is that this big architecture, what is doing is to take some kind of structured input and is somehow learning. The idea is that during the learning, the architecture becomes able to produce some feature vectors that has isolated the main properties that will allow the classification, the main properties of the input. So the idea is that the network produce some representation to feed in the classifier, that the classifier is able to, on which the classifier is able to work easily. And okay, this is, let's say, an abstract expectation, and you might say, okay, there are many networks, many different architecture, God knows what happens. But actually, in 2020, there was the paper of Dono and co-workers in which they observed this neural collapse phenomenon, in which they were saying, okay, let's consider a classification task on a big data set. But this classification task is performed on massively over-parameterized deep neural networks, so networks that are able to sorry, there is a question maybe.
Yes,
yeah,
sorry, just for the notations. For new, it's the layers. It's to indexing the layers, or
no, new is indexing the sample in the dataset. So, for example, I have 1,000 images. New is labeling, is, let's say, is the number of the
data,
images.
Numbers of data.
Yes, exactly, exactly.
Okay. Sorry.
No. Actually, speak out because I don't see the pictures sometimes, and so I might go on without stopping. So then this neural collapse phenomenon was observed in different architectures, and the nice thing was that in all these architecture, what was observed was that the network was learning the dataset, but the network was massively over-parameterized, as I was saying. So at some point, the network learned completely how to fit the dataset, so to label the dataset points. And what they observed is that in this regime, what the feature they tried to see what these features looked like, and they saw that when they fed, for example, if you imagine that you feed, for example, handwritten digits, and you want to see what's the representation of handwritten digits that the network is producing, if you feed, for example, various digits, the features are going to be points in some high-dimensional space that are concentrated in clouds, each cloud corresponding to a class. And these clouds will be centered around vertices of a regular simplex, so that essentially what this architecture is doing is mapping all these inputs in clouds that are as far as possible, putting in the same cloud elements that represent the same digit. Okay, so this was just to say that in this regime of the training, when the network has learned the rule, what is produced by the feature is a configuration like this, despite the fact that the inputs are, I don't know, photos of handwritten digits or images of animals or stuff like that. And so the classifier is going to face a classification problem on points in this kind of configuration, in which there are clusters, each cluster corresponds to a class, and the classifier is essentially to say, okay, given a new point, to which cluster the point belongs. Okay? So this was more a motivation than, I mean, we are not going to describe exactly this, but this was a motivation to think about which data set, which type of data set we might study. And so this is, let's say, deeper architectural, but now let's go to our model that, of course, is ridiculously simpler than this, but was somehow inspired by this kind of general framework. So first of all, the type of architecture that we are going to study is the simplest possible architecture. So it's just a perceptron, so one layer. And the reason, of course, is that this is the kind of things that you can try to analyze analytically. And you can think as this perceptron as just the classifier that is at the end of this deep network. So it's just a simple network that takes as input some x, applies some w, some matrix w of parameters to find, and then and then it's rescaled with the square root of d. And you want to find, so the parameters of your networks are just this w that have to be found somehow, and they are found with the same rule that I showed before. So you decide, you pick a loss, some function that define the performance, that measure the performance of this architecture, and you pick a data set. So you collect a data set of points, for example, with their labels. And what you do is to try to minimize the empirical average of this loss on the data set, that is the object that is here, minimize respect to w, and possibly, and this is a common practice in machine learning, add a regularization, convex regularization. This is something that should help you to achieve, it helps to achieve actually better performance if you tune properly this lambda. And it's something that sometimes if you have degeneracy, for example, if you have a flat region of the landscape in which you have many solutions that are equally okay, can remove this degeneracy. So the assumption that I'm going to make, that are going to simplify a lot my work, is that this convex loss, this loss is L is convex with respect to the second argument, and this regularization is also convex. this is not that exotic in the sense that the type of losses that are used in this classifier have these properties. But considering the simple structure of my network, in the end, my optimization problem is going to be a convex optimization problem because the parameter is exactly present in this second argument. So there are no problems of optimization, let's say, in this sense. And the type of regime that I'm going to study is the so-called asymptotic proportional regime. So I'm going to consider that the data set is infinitely big. The dimension of the input is infinitely large. But I will take the ratio between the size of the data set and the dimension finite. So n over d is going to be order 1. Okay, so this is as far as the architecture is concerned. And this is going to be the architecture that we are going to use through the talk. And if there are questions about this.
Just a question about, because you are using y and y, the other y at the top with the activation function. I don't know if in the minimization problem, the function of that introduced non-linearity is inside this.
No, this is a good question. Actually, the function that the function phi that is here,
yes,
is not in principle in this loss function.
Okay.
So it's something you might have the case in which it is, you might have the case in which it is not. The important thing is that overall the Gauss function that you are considering is convex with respect to this object. Okay. First thing. And second thing is that this nonlinearity is supposed to be fixed and given. You're not going to do any kind of optimization on it. For example, it might be a max or a sine or something like that. Okay. So you might, let's say, have it inside, but the important thing is that overall this function that appears here is convex.
Okay.
Okay. About the data set.
Sorry, Gabriele. Yes, just a quick remark. Does F stand for the Frobenius norm of the weight?
Yes.
Okay.
So in general, this is so it's the sum of the square of the elements of the matrix.
Okay. Thank you.
No, thanks. Actually. Okay, about this type of data set that we might study, you saw that there is this kind of neural collapse phenomenon in which the features are represented with clouds in space around some centroids. So the first idea that you might have is to say, okay, let's model our input of this architecture exactly in this way. So we consider that our architecture is going to work on an input that is made of k classes, and these classes lives in d dimension. Each class has some weights okay, and is centered around some mean mu k, and the distribution of each of the class around this centroid is Gaussian with some covariance sigma k. And each class is labeled with some special vector ek that is going to be indeed the label of the class. And so overall, what you get is that the input is going to be, so the data set is going to be produced by a Gaussian mixture. So by a mixture of all these Gaussians, each Gaussian has its own label. Each class corresponds to some mean vector and some covariance vector. Okay, so simplest possible assumption for the structure of the input. So just Gaussian. Okay, we'll skip this because otherwise I don't think we have time to get much in the details. We can go back to it. So this is the general setting. So simple with first one layer perceptron and this kind of Gaussian mixture model as data set. And the quantities of interest that we might take a look at are essentially these three. Actually, you can compute more than that, but these three are maybe the most important, that are quantification of the performance after the training. So suppose that you take your architecture, you train it on a data set of n elements produced by this joint distribution. And then you might ask, okay, what's the value of the loss on my data set that I achieved after the minimization? That is the first quantity that I call epsilon L. So this is the value that my, let's say, error measure achieve once I have done the minimization. So the minimum value of this cost function, if you want. So what's the training error? The training error is something that is maybe even more informative. It's just the probability that you make a mistake, that once you have done your training, is the fraction of misclassified elements of your dataset that you use to train the network. And the test error is the fraction of, is the probability of misclassifying a new data point that I generate with the same probability and that I present to the architecture. Okay, so there are three kinds of different errors. The first two are corresponds to the performance, if you want, of the architecture once trained on the dataset, and the third one corresponds to the performance of the architecture on a new data point that is produced and shown to the network. Okay, questions? It's just to fix a little bit what we're doing and what we're going to look at. Okay, if not, I will go on. Okay, so the interesting thing of this model, as I was saying, is a simple model that allows for a complete analytical treatment. And the complete analytical treatment, okay, this looks scary, but we will not go through the details of this, is done by using what is called a replica trick. At least we did it using the replica trick. There are other techniques, some of them relying on random matrix theory. And the interesting thing is that this is a high-dimensional problem. But in the end of the story, you can reduce everything to few order parameters, exactly as you do in statistical physics. And exactly as you do in statistical physics, here you're optimizing with respect to some quantity W that you can imagine as, like, I don't know, like the spin variables when you try to find the ground state of a spin system. And you can introduce some overlaps with respect to the signal of the data set, and describe everything with respect to this low-dimensional object, this low-dimensional overlaps. So in particular, there are these two quantities, QK and MK, that are low-dimensional matrices that takes into account, let's say, the overlap between, or if you want, the overlap between the W that you want to learn and the covariance in the case of Q of the cloud K. So QK is somehow quantifies the overlap between the weights that you are learning and the covariance of the cloud K. And MK quantifies the overlap between the weights that you are learning and the mean of the cloud K. So in the end, for example, if you have two clouds, you have two Qs in general and two Ms, or okay, two Qs and two Ms and so on. So it's just a number. The number of these parameters depends on how many clouds you have, and the dimension of these parameters depends on the dimension of the labels you want to produce. So, for example, if you are using scalar labels, so if your labels are, if your clouds are labeled like 1, 2, 3, 4, 5, these are not matrices, are just numbers. So Q is going to be L by L, where L is the number, is the size of the labels that you're using. But anyway, the important thing is that these matrices essentially capture the information about the overlap between the weights that you are learning and the structure of the data set. And they can be, and importantly, as it happens in statistical physics, they can be computed using some set of fixed point equations. Okay, the theorem below says exactly this. So there are some set of fixed point equation that allows you to compute these quantities. And through these quantities, you can evaluate the test error, training error, and training loss that I was mentioning before. So the performance of the network. So suppose that you have solved your problem and you have found these parameters that are perfectly equivalent, if you have familiarity with spin glasses, to magnetizations in physics and to the Q that appears in the spin glasses, so the overlap between replicas for people that know this. So once you have these order parameters, what you can do is to introduce two random quantities that I call omega and h that describe perfectly the statistics of the pre-activation in the case in which either you feed the network with a sample that the network already saw during the training, or with a sample that is new to the architecture. In particular, omega is exactly how the pre-activation behaves when you feed to the network a new data points that the network has not seen during the training. And in this case, you see that omega is some kind of is a Gaussian process, essentially. with minim mk and variance qk, covariance qk. And HK instead is a more complicated object, is exactly the pre-activation, the statistics of the describes the statistics of the pre-activation that you get when you feed in the network an element of the dataset that you used for the training of the network itself. And it's a more complicated object. It's intuitive in this sense because the W are correlated with the dataset elements. No? You use the element, the dataset to train your network to get a W, so they are not just independent quantities. And it's not obvious that you get, I mean, the statistics of this object is going to be non-trivial, at least less trivial. It depends, for example, on the loss. You see, it's an argmin of a quadratic form plus the loss that you used for the training. So it depends on this. So the takeaway, I mean, the take-home idea is you have fixed point, you can write down some fixed point equation for few order parameters. And with these few order parameters, you can characterize two random quantities, two groups of random quantities that describes precisely the kind of statistical behavior of the pre-activation that appears in the error. You see here in the training error, loss, training error, and test error, you have this pre-activation. But in this first two lines, the pre-activation is applied to an element of the dataset. And in the last line is applied to, is in a pre-activation generated by a new unseen sample. So once you have these two objects, you compute the average loss in the training error using HK in place of the pre-activation of the dataset. This complicated quantity here. And in place of the pre-activation that you get for new samples that you observe, you use this omega k. Okay, this is what I was saying. So it's a little bit involved, of course, because I mean, the entire goal is exactly to get the statistics of these pre-activations. But the crucial point is it is possible to do so, and it's possible to do so in terms of some simple low-dimensional order parameters that you can estimate. And it's a little bit more involved if you have many classes, but if the number of classes is order 1, you just repeat the operation. I mean, there will be a number of these fields equal to the number of clusters that you have. And in the figure here is a plot of some numerical experiment. Here we used a spatial loss function. It's called cross entropy. It's not that important. It's just this works, as I was saying, for any convex loss function. Here we picked one, and we saw how this thing was performing in case in which you have 2, 3, 4, 5 clusters. And so what is plotting on top is the generalization error. So it's the test error. It's the error that the architecture make once the training is done on new unseen example. And the training error is instead the error that the architecture makes on the dataset. And what you saw, okay, there are some continuous curves that are completely buried by points, and the continuous curves are the theoretical prediction, and the points are the result of numerical simulation. So there is a completely good agreement in this sense. You see, by the way, that the training error is 0. Okay, what is in the x-axis is the sample complexity. So it's the number of samples divided by the dimension. So you can imagine that at fixed dimension, but very large, what you're moving from left to right is you are increasing the dataset size. So you increase the number of points that you're using for training. And this explains why you have a region in which the error of the training is 0. It's a regime in which you have a few points, and your architecture is able to actually completely separate them and classify them correctly. At some point, the number of points of the dataset becomes too large, and your architecture is not able to perform a perfect classification, so it's not able to separate them perfectly, and must start making mistake, even on the dataset that you use for the training, and the error starts growing. Okay, and you see, okay, the same behavior is observed for different number of clusters. So the point here is to say, okay, this kind of a structure, this kind of let's say architecture is under control, and this kind of setting is under control, and we can actually compute all these quantities perfectly analytically. And actually, there's been a line of works that led to this. Okay, we did the case with the general number of clusters, general covariances, and so on, but you see that there is a list of people that worked on this Gaussian mixture model, typically with 2 clusters or with homogeneous covariances or in other settings, and we're able to achieve an analytic control of this. So let's say this was done by us, but by many other people in different ways. Okay, I don't know if there are questions on this.
Actually, it's not a question, but just the V, it's
V is another.
What? Okay,
yeah, this is a very good question actually, because the meaning of V depends a lot on the loss that you use. The meaning that is the intuitive is an auxiliary quantity that appears when you do the calculation. You need to introduce this V when you make your let's say center point equation. It's again an auxiliary quantity. In a sense, you see in this. Appears as some variance of the quadratic part that you have to minimize to get properly this H. But the physical meaning of this the intuitive meaning of this V depends on case by case, I would say. At least I don't have a general answer for this. There are situations in which express some, let's say, if you have some kind of loss, express, I don't know, the number of elements of the solution that is 0 or things like this, but depends on the loss and on the regularizer that you're using. So for this, I don't have an intuitive answer, sadly. Okay, so once we have done all this analysis, theoretical analysis, we were saying, okay, what about the real problem, the real things? So are we doing this in a too abstract way? Is this useful to understand reality? And so we run this simple experiment, and using this model is called a random feature model. That is, if you want, the simplest possible step towards the more complicated structure. So we were saying, okay, let's do the following. So we consider this architecture, and this architecture works in this way. We feed an input in this architecture, the first layer, and to get from the first to the second layer, what the architecture does is to multiply the input by a random matrix F that is not learned. It's just the random matrix that is decided, Gaussian random matrix that is decided at the beginning and fixed. So it's a random matrix decided at the beginning. And then a nonlinearity F, for example, in this example, we used F, that produce a vector in the second layer, in the hidden layer. And this hidden layer vector is going to be fed in our classifier, and the classifier is going to be trained. Okay, so essentially it's like considering it's a training, it's a network in which you don't do any training on the first step, on the first layer, to go from the first to the second, but you do the training on the parameters of the last layer, the classifier. So you don't make learning here, but you do learning here if you want. So the second layer is exactly the kind of architecture that I was showing you before. And the first layer uses this random feature matrix multiplication. And we use this architecture to study actually real image, dataset from a picture from real datasets. So for example, from NIST, which is the dataset of handwritten digit that I showed you before, or fashion NIST, this is the dataset of clothes and accessories. And we were saying, okay, we would like to train our classifier to distinguish, for example, even by odd and even numbers, or clothes and accessories. And everything had to be done training the second part. So of course you can run your experiment and see how, once you do this training, things go. And this produce these plots. Okay, there are different curves because each curve depends on the size of the matrix F that we use. No? And the experimental plots, the result of the experiments are the circular dots, if you want. They are here. This is for NIST, this set is for NIST, and this set is for the second column is for fashion NIST. And then what we say is, okay, let's do this kind of brutal assumption. Let's assume that whatever is produced here in the hidden layer, is a Gaussian mixture. And we just compare what comes out, like the performance of the network that I described to you, what the performance that the classifier would have had if I had fed the classifier with a Gaussian mixture with the mean corresponding to the means of the feature produced by the different classes, and the covariance of the feature produced by this random projection. I don't know if this has been clear. So you do this, you have your data set, and for example, you take all the even numbers and you look at all the x that you produce with the even numbers. That is one of the classes through this law. And then in this set, you compute the mean and the covariance of this set. And you brutally approximate this distribution, that is empirical distribution, by a Gaussian that is the mean of the empirical mean that you observe and the covariance of the empirical distribution that you observe. This is, of course, a brutal approximation. You are neglecting everything possible non-Gaussian, and you do this for all classes. All classes are replaced in the theoretical analysis by an equivalent Gaussian that is the mean and the covariance of the dataset. Okay? And if you do so, you can produce some theoretical prediction. And the theoretical predictions are the lines that are represented here. And you see that the agreement is not perfect. Actually, in some cases, it's quite bad, like here. But it's not completely off. So this is like saying, approximating what is produced, the feature produced in this second layer, just by random projection and nonlinearity with the Gaussian mixture is not such a bad idea. Somehow it works. But the thing is that, okay, it works, but not perfectly. But anyway, these kind of things, I mean, it was not just our paper. Many people realized that this hypothesis was actually, hypothesis of having Gaussian features was not that bad, and boosted a lot of interest in this kind of thing. Is always true. Is it possible that if I feed to my network with a distribution that is anyway generic, what goes through is just a mean and covariance, and in the end, it's like working with a Gaussian or a Gaussian mixture. And it came out that actually sometimes this is true, in the sense that, for example, okay, we'll not go through all of this, but for example, in a very recent work, there was this recent work of Montanari and Said, in which they show that if the distribution that you feed in your network, if the distribution that you feed in your network have marginals that decay fast enough, that are essentially sub-Gaussian marginals, to be precise, then you can pick the distribution that you are feeding it in the theoretical analysis to theoretically predict how your machine is going to work, your one-layer machine is going to work. You can replace the input distribution with a Gaussian distribution that's the mean and the covariance of the distribution, the original distribution. So instead of working with a complex whatever distribution your dataset might have, you can do this replacing and say, okay, let's assume that this is a Gaussian with the mean and the covariance of the input. But this requires that your dataset input, I mean, your dataset distribution is some kind of a steep tail. I mean, they go down quite fast. So in general, there is this feeling that maybe there are cases in which you can do this replacement. Actually, it is also known that you can not always do it, but maybe in many cases, this replacement is not that bad. So if you have a mixture of different distribution that have some mean and covariance, you can maybe replace them with a mixture of the equivalent Gaussian in which you have matched first and second moment. Okay. I don't know if this is there are questions about this, like about at least the problem and the idea that
it's not really a question, but just to understand more. So your data set, I mean, in practical, your data set is like individual cases or like probability distributions. So initially, so.
Yeah, the data set is generated in this way. I have this if you want, you can proceed in this way. For example, you want two clusters to produce a data set that represent two classes. Each class corresponds to a Gaussian distribution with a mean and the variance. So you simply produce points in which, with, for example, the probability 1/2, you sample from the first clouds, and then you assign to the point that you sample label +1, meaning is in the first cloud. And with probability 1/2, you sample from the second cloud, so from the second Gaussian, and you assign to it a label that is, for example, -1. So the dataset is going to be a sequence of all these points that you sample, with some number or some label that tells you from which of the cluster you sample them. They can be, for example, -1 or +1 or 1, 2, 3, 4 if you have 4 clusters or so on. So the dataset is just a list of these numbers with the proper labels and corresponds to the points, to these points. So for example, this is the dataset, if you want, in which the X are the points and the color here represents the label that they would have in the dataset.
So what do you replace with Gaussian distribution in this case?
So, for example, suppose that you are working on with MNIST. In that case, you start with something that is a collection of pictures that is labeled with a number, and the number is what the picture represents. For example, a picture of a 2 and written 2 is labeled with an actual 2. That is the number that is represented in the picture. So what you do is that you collect, for example, all pictures that represent a 2.
Okay.
And you construct the X corresponding for each one of them with this operation. You multiply the picture by a random matrix, and then you take this nonlinearity of it. Because the picture in the end is a vector of values between 0 and 1. It's a black and white picture, so it's a vector of numbers. So you produce this number X, and so you will have all the X's that comes from pictures that were representing 2. And so for all these pictures, I mean, from all these X's, you can compute empirically the mean and the covariance of this collection. No? And you say, okay, I don't know what distribution they have, but I say that this thing, that is the representation that I give to the all 2's, is approximated by some Gaussian cloud with the mean, that is the mean of the data set that I obtained and the covariance of them. But I don't actually, of course, it's not obvious. It's, okay. It's not obvious it's a color. Okay.
Thank you.
No problem. Okay, so this was the question essentially, and this actually goes make us go in the core of the talk, because this was a question that was asked: is it possible to do this replacement and things that somehow always work? And there were some numerical experiments in this direction. So, for example, what if I do the operation that I was exactly describing here with more complex databases? And what in this paper, what they did was more or less what I was saying. So they took a database that was actually a database of the Cipher10. It's a database of pictures of animals, planes, cars. So it's a much more sophisticated database than just handwritten digits. And they tried to train a network doing exactly this kind of approximation. So either feeding the correct dataset or feeding to it some Gaussian clouds that have the mean and the covariances of the classes of the dataset. So you replace essentially the dataset with let's say another dataset that is the Gaussian approximation of the original genuine dataset that you have, in which essentially you have dropped all higher order cumulants of the distribution. So for example, I have all images of horses, and I just look at the average of the picture of horses and the covariance of the picture of horses, and I generate the Gaussian cloud that should represent the horses. That is the mean and the covariance of the two images. And of course, what they saw is that performance, if you use the Gaussian model, are very bad. And the network, this is what happens in the performance of the network during training. At some point, the network simply, if you use the Gaussian approximation, that is the lower curve, the network simply does not learn anymore. It's not able to perform better than something. Instead, if you feed the entire distribution, I mean, if you feed a good data set, you achieve very high performances, meaning maybe an obvious fact, but okay, it was just a test to see that actually you can, the network learns these high order cumulants and use them. This was done with a deep network, not with the one that we were discussing. So it was done okay with this ResNet 18. So at this point, we were a little bit disappointed because we were saying, okay, all the results that we have are for Gaussian. What if we try to enforce the fact that actually these clouds that represent, that generate the dataset have power law tails? And but this was analytically a little bit challenging, and we used a trick essentially. And we said, okay, instead of assuming that the clouds are just Gaussian, what we can do is to say we replace these clouds, each cloud, with an infinite superposition of Gaussians. So what we do is to obtain, okay, so P of X given mu is, for example, the probability distribution of one of this cloud is a probability distribution of a cloud of a class centered around mu. And this is obtained taking the expectation of a Gaussian, where the expectation is taken respect to the variance of these classes, of these Gaussians. So essentially, this distribution of P of X is obtained taking the superposition of an infinite family of Gaussians, each of them with, let's say, with its own variance, and the variance, the covariance, is sampled from a distribution rho. Okay. So in a sense, we are replacing the simple Gaussian. This in the theoretical model. I'm saying, okay, I consider a case in which my data set is constructed from, is obtained sampling from clouds whose distribution is, each of the cloud is an infinite superposition of Gaussians, in which the variance, if you want, of these variances of these Gaussians is random, and there's some measure by rho. And this means that, first of all, overall, the covariance of all these objects is not just a number. I mean, it's not just delta, but it's the expectation of this delta. It's the expectation of the covariances of the variances that these Gaussians have. So here I'm considering Gaussians that have diagonal covariance with prefactor delta. Okay, and so this also means that if I'm able to control this situation and change this density, I can also have the situation in which this delta, the expectation of this delta is not finite. And this means that these clouds have infinite covariance. This is an interesting case. No? But more interesting, if I make this replacement, I can also obtain power law tail distributions. For example, this is a way to represent the Cauchy distribution in one dimension. I can practically superimpose with a proper density of delta an infinite number of Gaussian. I get the Cauchy distribution. But let's say that, as you know, of course, there's infinite variance and so on. So it's a trick to represent distributions that have power law tails and possibly infinite covariance as a superposition of Gaussians. And of course, includes a special case, the case in which you have just Gaussian, because if this rho is concentrated on some specific value, you get a Gaussian. No, it's a Dirac delta, you get a Gaussian. Okay, questions about this? Okay, this was, again, just a theoretical model to see what happens. Can we treat this case? And let's see what happens when I introduce power law tails. And okay, this was just a pictorial example in which I pick a density of these variances. And I say, okay, if I pick this specific density, I can generate a family of distribution that is Cauchy-like, you see, as some depends on two parameters, in which one parameter gives me the scale, like in the Cauchy distribution, and the other parameter gives me the rate of decay of the tails. And depending on the parameter that I choose, I can have a finite variance or an infinite variance. So the task is at this point, in this setting, can I do the calculation? Can I make the same thing that I did for the Gaussian case? Obtain, for example, formulas that provides me the test error, training error, and so on. Okay, this slide is just saying what I was anticipating to you. So what we did was exactly this, was to replace the clouds. Instead of having Gaussian clouds, we consider the case in which we have these super statistical clouds, as we call it, because in physics, this construction is sometimes called the super statistical construction. And we consider two clouds, for example, in which points are obtained in each cloud with the same distribution that has this form that is in the box. So each cloud has a distribution that is a infinite superposition of these Gaussians, with some measure of the delta, that is the covariance of these Gaussians. And again, we do the same task. We try to minimize, we try to fit these clouds with our one layer perceptron and see how this will perform. Okay? So we'll try to find the minimum of our risk and see how things go and compare maybe this with the case of Gaussians. Okay. So actually you can, the interesting thing is that you can reproduce the same calculations. They are a little bit more tricky because you have to take into account the fact that you have this variance that is random. But actually you can get the same kind of, let's say, information. So you can write down equation for some h and omega that are some random variable. Here there is an h plus minus and omega plus minus because I'm considering the case in which there are two clouds. One is called plus and the other is called minus. So for each of them, there is, let's say, I mean, the pre-activation that I getting an input from each of the cloud is labeled with the sign of the cloud. And exactly as in the Gaussian case, you can obtain a statistical description of the pre-activation that you would get if you feed your network with a point of your dataset, that again I call H. And the statistics of the pre-activation that you would get if you feed your network with a new unseen sample that they call omega. And exactly like in this case, once you have the characterization of these two quantities, you can compute your training loss, your training error, your test error, exactly like in the other case. The only thing is that the equation, the fixed point equation to find these two random quantities are more tricky. And interestingly enough, these two fields, in particular the field omega that describes the pre-activation in case you feed with a new sample, is not Gaussian anymore. Inherit the structure of the dataset. This dataset was superposition or infinite Gaussian, and so that in the end was, I don't know, Cauchy-like, and this omega is going to be Cauchy-like. Okay, but the philosophy is the same. You try to write down some fixed point equation for some order parameters that represent the overlap between what you want to learn and the structure of the clouds, their mean in particular. And then you write down some equation for these two pre-activation, H and omega, and use these two pre-activation, the statistics of these two pre-activation to compute the average training loss, the average training error, and the average test error. So what we got, so from now on, less mathematics, a little bit more plots. So I think it becomes lighter. Just before moving to the results so that we obtained in this setting, I don't know if there are questions. Please ask if you don't. So you see that, let's say that the type of idea is, can we generalize, relax the Gaussian hypothesis and consider clouds that are not Gaussian, but power-law-tailed, and see how they perform, how the architecture performs on this power-law-tailed distribution? And the answer essentially is yes, within this family of superstatistical distribution. And this was interesting because, for example, we could compute things like this. So, for example, suppose that we have clouds that have all the same covariance, and the covariance of the cloud is just identity. So you are in the setting in which you have two clouds of points and you want to classify them, to learn how to classify them. And they both clouds have covariance 1, I mean 1, equal to the identity. And but because, of course, in our model we can tune also the tip of the tail, you can consider a family of cloud distributions that have the same covariance, the same mean, but different tails. And this is a way to check what I was saying before. Is first and second moment enough, even in this simple setting, to describe what's going on? Because all the members of this family, so for example, this is, of course, an expression is a little bit convoluted, but the question that I write here in the below the plot is a distribution, for example, of a cloud centered around mu. And depends on the parameter A. For all A, this distribution have the same mean and the same variance, the same covariance. So one question might be, depending on A, do I get different performance of the network? And actually the answer is yes. So depending on the way the tail goes down, you get different kind of test error. I mean, different curves for the test error, different performance on your training set, and even different average loss once you have done your minimization. And this is a strong indication of the fact that the tail matters. Even in this very simple architecture, in very simple setting, the fact that you have a power law tail does not give you any Gaussian universality. You need to see, you need to use the information of the tails, even in this super simple setting. Because if you compare the Gaussian case with the other cases, you have different curves. So in all these plots, the red curve would be the Gaussian that has the same mean and the same covariance of these clouds. And the other curves corresponds to different exponent A of the tails. And so you see the plots are different. And actually what came out is that in the case in which you have power law tail, this is something that statisticians know actually, the variance is not a good measure of this of spreadness. And a better measure is the mean absolute deviation, so the average distance from the centroid. So all these clouds have the same covariance, but they have different mean absolute deviation. And what happens is that the machine performs better on the ones that have a mean absolute deviation that is smaller. That in this case are the ones actually with the power law tail. It's counterintuitive, but this is what happens. Okay. Okay. The nice thing of the family of models that we are considering is that we can consider the case of infinite variance as well. And there are actually no kind of restriction in running our equation and try to have a theoretical prediction and the theoretical grasp on the case of infinite variance. Of course, in this case, let's say the opposite happens as before, like the Gaussian is the one that has lower error, and as soon as we switched on an infinite variance, okay, in this plot, what we do actually is a mixture of a Gaussian, we consider a mixture of a Gaussian and an infinite variance distribution, and we are tuning the contribution of the two. So when we have the pure Gaussian case, we have the blue curve, and this is the test error, so it's the performance of the network. As soon as we switched on the contribution that comes from a distribution with infinite covariance, the error increases and the performance gets worse and worse. And the more this contribution is present, worse it is. But this is maybe expected in the sense that we are trying to fit a cloud that is infinitely scattered, let's say, on average. And okay, so this was just to show you that infinite variance is also achievable. And okay, last thing that I want to mention, consider that the time is over, is that we can do also another kind of calculation that is very interesting. And that is, we can compute the separability transition. So what's the separability transition? This is something that is related to the task that we are doing, in the sense that we are searching for the best way to classify points in this high-dimensional setting. And you can think of this as searching for, if you, for example, have two clouds, searching for the best plane that cut the space in two parts and separate the elements of one cloud from the elements of the other cloud. Okay? And one can ask, okay, depending on how many points I have, and I am in dimension D, and I have n points, is it possible or not to find a plane that goes through space and cut into the two groups in a way that all points that are in one class are on one side and all points that are in the other class are on the other side? This is like saying I want to find an hyperplane that classify a dataset, my dataset, in a way that I make zero error, because I completely separate the points of one class from the points of the other class. Is it clear, this question that I'm asking? So I'm asking, depending on how many points I have, once I generate these clouds, I have two clouds in high dimension, and this classification task this time is, what I'm trying to do is to find a plane that cut them in two parts. To cut them in two parts, separate them perfectly. And such that, for example, like in the picture, the points of one class on one side and the points of the other class on the other side. So what is known is that if you, for example, consider two Gaussian clouds, there is a precise formula for the number of points n over d. I mean, for the simple complexity, because we are considering d that goes to infinity, so the number of points has to be considered scaled with respect to d. So for the value of n over d, where you can, the maximum value of n over d, where you can separate these two clouds. And this formula was obtained by Mignacco, Giacalà, Lu, Urbanians, de Borva, 2020. And if the clouds have a variance that goes to infinity, if they have Gaussian clouds that have variance that goes to infinity, this critical value goes to 2. That is something that people know because it's called the covariance transition. Okay, what we did was to find this maximum number of data points that you can have in d dimension that are separable in the case in which you have these super statistical clouds. So clouds that are obtained from infinite superposition of variance, and therefore also power law, including therefore also case of many power law distributions. Okay. And what we found is that the criterion is the following. So alpha, you have to read in place of alpha n over d. N over d is to be smaller than this object here that depends on this parameter theta. And okay, it's some kind of formula. So, but anyway, it's a kind of explicit formula that you can solve. And so for any distribution of your variances, you can actually find the value alpha star where you have separability. And what you see is that, of course, this value alpha star is going to be larger than the covariance transition. It's always larger than 2, because 2 is the case in which points are completely uniformly, completely scattered in the plane without being concentrated, without any structure. This formula recovers the case in which you have Gaussian clouds, when of course you assume that the variance is concentrated, the variance of the single contribution, the distribution of the variance is concentrated. And okay, this result was neat, was interesting because it was a close formula result that we had for this separability transition. And we found in particular that in the case that we investigated that, okay, the transition was above, as I was saying, the Gaussian limit case. And of course, in the case in which you have no covariance and infinite scale, you have the result of cover. So the interesting, what I want to say with this is the fact that if you have no covariance, this is not like having points, of course, scattered everywhere in the plane. And what you have to search for is another scale parameter in your distribution that determines how spread your distribution is. And it's going to be that parameter that is going to tell you how far you are from the case of cover, in which essentially points are just randomly scattered in the plane with no structure whatsoever. Okay, I've been very sketchy on this, but in case, please ask me a question after we finished. Okay, consider the time is up. I will give just some conclusion. So what we observed was, okay, first of all, we showed it was possible to have under control the Gaussian case. This was done not just by us, but by many people actually that contributed in many different ways. But in the end, the Gaussian case is essentially solved. What we saw also, though, is that this Gaussian universality is quite fragile in the sense that when we move to the case of distribution of the power law tails, all these quantities, like that measure the performance of your architecture, takes different values and depends on aspects that are beyond the mean covariance of the data sets, of the data that you use. And we found an explicit formula for the separability threshold in this setting, superstatistical setting. And this means that we found an explicit formula that is able to tell us how many points in the infinite dimension at max you can linearly separate in this infinite dimensional limit. And actually, there are other two things that I have not time to discuss that are related to the fact that this setting was consistent with the Gaussian case in the fact that the role of the regularization that I mentioned at the very beginning of the talk is important in the sense that tuning the regularization, we can actually achieve better performances in training. So there is a value of this regularization lambda, that I just put there in the empirical risk minimization that actually can give you very good performances on the best performances in the test error, and you can use this degree of freedom to achieve this optimal performances. And okay, the random number case was not discussed, and in case I can chat after the end, now in this question session. Thank you for the time, for attention.
Yeah, thank you very much.
Thank you very much, Gabriele, for the talk. So yeah, it's time for questions. Are there any questions?
No, Andrea is here.
Matteo, there is some...
Yes. Yes, so, okay, yes. So, okay, maybe I can start with one question. It is about these distributions that you have shown, these P of X mu, that were depending on two parameters, A and D. And I do not know if it is related to the way in which they enter in your framework, but there is an interpretation that these kind of generalized Cauchy law have, and you can interpret them as projections of the uniform measure over the D sphere onto some plane, some kind of stereographical projection, in which D is really, I mean, the exponents that you have there have to match somehow the dimension of the sphere in which you have the uniform measure, and the constant in the denominator term, the 2c in this case, is related to the distance of the center of the sphere from the plane onto which you project. And given that you are dealing with Gaussians, I was wondering if this somehow spherical underlining structure was playing some role. I mean, it's kind of speculation. We can discuss further, more precisely, this projection. But
okay.
Yeah.
No, for us, the reason, I mean, we didn't have in mind this geometrical construction. The only reason we picked this kind of family was the fact that this family had had just two parameters, and with these two parameters we could control two things: the scale C and the power law decay of the distribution. And consider the fact that our formulas were, let's say, our formulas were for any distribution of this variance of the Gaussian. I mean, we can solve whatever distribution, for whatever distribution, but in this case, we had just a small two-dimensional space, let's say, of parameters in which we can try to see what happens when the scale diverge or the power law decay becomes infinitely steep. That was the only motivation, just to have something simple, and also something that was in some regime. So in the case in which you take C equal to A minus 1, and then you send A to infinity, you recover the Gaussian case. So this was also another thing, because we want to deform, let's say, the Gaussian case to something that was power law distributed. And this was, let's say, comfortable choice, but there was no other specific reasons. It's just that. It's just to have.
Well, another natural choice is to use Levy distributions.
There's something that is a special case of this, no? But actually, you see that in this case, I have also here I am in high dimension. And so here there is this D over 2. So in the end, the tail of this thing is 2A minus 1 in the radial direction. So yeah, depends like how you interpret this. If you have you can put your A in a way that you have some 1 over x squared, let's say, in the radial direction.
Admittedly, there is no good reason for using Levy distribution unless you convolute your objects, which is not the case here. Otherwise, they are just ugly to work with because they are not very explicit. They are only nice because they are stable in the sense of stability. So if you don't use stability,
yes,
no choice, but
yes, but indeed
overlay laws.
This is indeed something that, from the numerical point of view, enters in the game, because when you have to integrate, for example, this quantity, I mean, when you want to solve this problem, you have to take these expectations, and the expectation depends on the distribution of the variance is big, and I mean, this can be, let's say, against Levy. I mean, in the case of Levy, you can do the integration. This can be numerically a little bit tricky. This is what I'm saying, because if you use Monte Carlo, you have to sample the tails. If you try to do a quadrature thing, you have somehow to split the domain in a smart way to have a stable integration. So, but this is just a numerical issue that we only had in the case in which the covariance was infinite. But aside from this, everything worked.
Further questions?
Maybe I can ask some question. Just about, because from the beginning, all the studies is based on the architecture that you choose at the beginning of the neural network. So
Yes.
I am curious if you try to modify something on this and like see if
this
you
is
get the same results.
This is a recurrent and also interesting thing, in the sense that what people do from an analytical point of view typically is either use straight away this architecture or use architecture like the one that I show you here, in which anyway the training is on one layer, you know, and you don't have, let's say, so the first layer, this is already deeper, but it's a fake deeper in the sense that the first layer is not trained.
Mm-hmm.
There are cases in which people did some kind of training on two layers, but putting some constraint on the nature of the coefficient of one of the two layers. And so in a way that they avoid the complication that might come to have too much freedom in both layers. And there is a nice line of research of Kabashima, which actually was studying the case in which you had deep architectures. But the complication there is that you have somehow to define an order parameter. So the order parameters that I showed you that define essentially the statistics of the output, you have to define them for each layer.
Mm.
So if you have, I mean, many layers becomes very heavy, becomes to do the calculation and also. And what he was doing, if I remember correctly, was to try to define a limit of infinite depth, so that actually, instead of having an infinite number of these parameters, you have a function of the depth, something like this, and you try to optimize on these functions. But this kind of, for this thing, this is something we could think of to see the effects of let's say, of deeper architecture, but we didn't try. We didn't try for this problem. Thanks for the suggestion. Anyways. So good point.
Is it conceivable that a true deeper layer would, for example, in the digit case, how would it work? Say that we agree on the fact that on the digit case, 8, 0, and 9 and 6 are similar to each other, and 1 and 7 and 4 are similar to each other. So it's like if the things are not really as vertices of a hyper simplex, but they are kind of first scattered the line ones from the curved ones, and then those are scattered within. How do the layers work? Is the first layer that makes the first separation and the second one that makes the separation between? Or is the converse?
This is a good question that I don't know. I honestly don't know. It's something that I don't know, also because I don't know if this depends on the kind of filters that the different layers apply. if you have, you know, some layer that looks at angles or difference or edges, or because some of these modern architecture do this, no, this convolutional neural network do this, they apply some filters and search for, let's say, patterns that are repeated in. So I don't know how this is a good point, actually. I don't know if people did some experiments in this sense. For example, if this depends on the order of the filter that are applied or not. But the story of the clustering is interesting also because it doesn't depend much. For example, in our experiments, what we did, this experiment is exactly in this figure. We did even versus odd. So it was not much related to the shape of the numbers, let's say. It was just we decided to do this. And this was done with one fixed random projection. And anyway, I mean, it's not like the test error is like 20%, so it's very bad performing, but it's learning something. This is what I'm saying. It's learning something, is able to do something. But no, it's a good point. I don't know.
Not clear if it is learning perfectly some digits and very badly some other digits.
No, I don't know this.
Because 20% may be one of those.
It's good.
You have to
good
check.
Point.
You can check.
I should have checked. We should check. Yes. Yeah, we should check. Divide by classes, like by genuine classes. What are the performances? Yeah, it's true. Actually, it's a good point. We should check. I should ask the.
I have an appointment in a place which is 40 minutes away at 4 o'clock. So
okay.
Okay.
But don't forget that I'm still following you.
Okay. I know.
Thanks again for the talk. See you,
Andrea. See you, Andrea.
Thank you, Steve.
Thank you for attending. Maybe from my side, just one final question about the separability question at the end.
Yeah. Please. I know that I've been super sketchy in discussing.
Okay, I have some general thought about this, but if we are asking that there is some hyperplane which separates the two classes, it means that like the how we call the prediction function is like linear in some sense. So I don't know. I just to try to organize my thought about this question of having some hyperplane to separate two classes, because in this, if there is some hyperplane that separate two classes, I think we have other methods that, rather than neural network to work with, like for example, gradient regression or something.
Okay. Indeed, this maybe was not very clear. The point that I want to make was just that in this setting, using the equation that I used to solve this problem in a dimension, I can get the point where I can do this kind of separation. I was not proposing that this is the ideal way to do it. I mean, maybe I was just saying that you can find a point where. What I'm doing here is not that I'm separating the distributions, of course. I'm saying I sample from the distribution, so I have points. And I want to find a plane that separates the points of one distribution from the points of the other distribution. So depending on how many points I have, I might have actually infinite planes that do this, like in this picture in which any and then at some point, there will be no plane. If I increase the number of points and I sample and increase the number of points in this picture, at some point, it will not be possible anymore to separate them because they will be mixed and the tails of the blue cloud will mix with the red cloud and will not be possible to separate them. So, so my point was to say, okay, when this happens, if I fix the dimension and the dimension is very high, or at least because of course this is all in infinite dimension, what's the ratio n over d for d going to infinity where this happens? This was the question that I was asking. So, how many points I must have so that I cannot, on average, do the separation, if you want, where these things stop being possible.
So in some sense, these points get mixed in some sense, but you couldn't separate anymore by some.
Exactly. Like, of course, in 9 dimension it's difficult to picture this, but this distribution have not found support. No, I mean they are supported. Their support is everywhere in the space. So at some point in sampling, they will not become. They will mix up. I mean, there will be whatever close at any distance from the centroid of the red cloud, there will be a point of the blue cloud. With, of course, density is infinitesimal, but still enough to make a mistake. And instead, I want to find a plane that actually makes no mistake once I do this separation, given some set of points. And in the end, the criterion is this one. But okay, it's not very beautiful, but it is what it is. And this was interesting for statisticians because it's related to the story of the maximal likelihood estimator existence, of course. Because the maximal likelihood estimator is exactly this hyperplane. In a sense, I mean, it's not the hyperplane, it's like the best hyperplane that you can find to make a separation. But when you can actually separate them, what happens is indeed that you have many possible solutions. So the uniqueness disappears. And statisticians were really interested in this separability transition for this reason.
Thank you very much, and thank you very much for the talk. It was very clear and well presented. Thank you very much.
Thanks.
Okay, so if there are no other questions, I would like to thank again Gabriele and remind you that we will end this session in 3 weeks with the last talk of the year. Okay, I think
thank you.
That's it.
Thank you again. Thank you for having me here.
Have a good day.
Have a good day.
Thank you.
Bye.
Bye-bye.
Grazie, thank you.